In this video, we present our work on enabling faster locomotion of planetary rovers with a mechanically hybrid suspension, a work conducted by EPFL and Tohoku University's Space Robotics Lab. The rocker bogie or RB suspension has been widely used by most existing planetary rovers. The RB suspension is a very robust, fully passive, inelastic suspension designed for operational speeds below 10 centimeters per second. At higher speeds, the structural integrity of the suspension and the stability of the robot cannot be ensured. However, future missions demand a faster and more efficient exploration of planetary surfaces, which are often characterized by unstructured and loosely consolidated terrains. Fast lunar vehicles are not completely new to the space exploration scene. Unlike the RB suspension, Apollo's lunar roving vehicle or LRV inherited a suspension with elasticity and damping, similar to those frequently used in conventional road vehicles. Thanks to its ample power reserves and direct human piloting, the LRV achieves speeds far exceeding those of contemporary lunar and Martian rovers. However, quantitative data on the suspension performance were never collected during Apollo or lunar missions. We therefore performed a series of simulations to understand how the combination of speed and a lunar-like gravity field affect the performance of passive suspensions when traveling 2 orders of magnitude faster than current planetary rovers. And unveiled for the first time the potential improvement and limitations of adding passive energy dissipation devices to conventional free balancing suspensions. For this, we compared the performance across 3 different types of passive suspension configurations: a dependent rigid suspension simulating the effect of a rocker, an independent elastic suspension simulating that of conventional ground vehicles, and a novel suspension configuration based on the combination of dependency and elasticity that we named mechanically hybrid suspension or MHS. And we integrated these 3 types of suspensions within a new rover prototype called Explorer-1 or EX-1 for short, in order to test their performance in more realistic scenarios. The first tests we conducted were aimed at evaluating the contribution of the independent shock absorbers when moving at high speed over unconsolidated, slightly uneven terrains. In this case, the rover was commanded to follow a 10-meter straight trajectory divided into 3 phases: an initial acceleration from 0 to 1 meter per second, a steady-state travel at a constant speed of 1 meter per second, and then a final braking maneuver from 1 meter per second to a full stop. We performed at least 6 runs with each suspension configuration while the terrain was raked between runs to guarantee the repeatability of the results. Maximum and minimum values and the mean of the standard deviation of the vertical accelerations experienced by the chassis is presented in this table. Results confirmed an overall reduction of the vertical accelerations experienced by the chassis when the MHS is used. This is particularly significant during the acceleration phase, where the rover experienced greater vibrations due to an observed increase in wheel slippage. In a second experiment, the rover was commanded to drive its left side wheels over a 10 cm rock at varying speeds. In this case, the addition of elasticity and damping provides a clear advantage in mitigating loads and vibrations, so we wanted to observe the potential benefit in the addition of dependency by comparing the IE with the MHS configuration. Both configurations successfully overcome the obstacle at 20 centimeters per second and 50 centimeters per second, but it was only with the mechanically hybrid configuration that the rover was capable of seamlessly negotiating the rock at 1 meters per second. The mechanically hybrid configuration showed a significant attenuation of the vertical accelerations experienced by the chassis when overcoming the rock beyond what could be achieved by the independent elastic configuration in this case. The suggested mechanically hybrid suspension improves stability and successfully isolates the chassis of the rover from unwanted vibrations and impact loads beyond what could be accomplished with either of the other 2 commonly used passive configurations, particularly at higher speeds. It should be noted that no traction or trajectory control was implemented during the study. Thank you.